All right, so welcome to lecture 20 for MT225, our last class prior to our second exam. So Wednesday is our second exam, and I'll have a few things to say about that here in a moment. Um, Homework 8 was posted last week. That is a bonus assignment. It's due on Wednesday, so sometime Wednesday evening prior to midnight would be acceptable there. It is a bonus assignment, meaning that if you don't turn it in, it's not going to hurt you. If you choose to turn it in, then it can replace, if you do better on it than a previous homework assignment, it'll replace that grade. In fact, it's previous or future, the way that I've got it set up in the spreadsheet. So could potentially buy you out of a future homework assignment, although we really don't have that much in the way of homework assignments left. I think we have 2 homework assignments left. Homework 7, for almost all of you, homework 7 has been returned. I've had some problems reportedly with email going to Google from MVCC, so going to Gmail accounts. So check your student account. I have, it's a weird thing. MVCC's server is apparently recognized as a source of spam to Gmail. So it tends to drop messages without even telling you that it's filtered them. So I'm going to return everything officially through your student account because I'm guaranteed delivery there. So check that. There's one exception. One of you will not have gotten your homework assignment back because I haven't finished grading it yet. I'm still kind of adapting to how long it takes to grade homework assignments in this format. So don't worry about that. If you haven't gotten email from me yet and you did turn in an assignment, you'll be getting something back this evening. I'll finish that up before too long tonight. Exam 2 is on Wednesday. And in keeping with a similar structure to what we would do if this was an online or a not an online class, if this was just a regular class, Wednesday will be the day for the exam, sometime early on Wednesday. So sometime probably early Wednesday morning. Uh, I will post the exam on the website. Uh, I'm going to leave it to you essentially to work it out as a sort of honor system sort of thing. You can fill out 2 index cards. It's kind of run it the same way we would run the exam in class, 2 index cards on this one instead of 1. So you can put anything you want on that 4 inches by 6 inches. And I'll post it on the website. It's due to me by email before 11:59 Wednesday night. Just to be clear about the ambiguity of saying due on midnight on a particular day. It's never clear whether it's that day or the previous day. It gets confusing. So 11:59 p.m. on Wednesday night is the due date. There is no official class on Wednesday since we're doing the exam, but during our class time, I will be online at the regular meeting site for any questions that might come up or anything like that. So if you run into an issue, something is hard to interpret, or you're not quite sure what something says on the exam, that would be a fine time to guarantee that I'll be available to ask those questions too. And that sample exam 2 has been posted for just a little less than a week now. So before we proceed to anything else, we have homework 8 out, the bonus homework assignment on frames. Does anyone have any questions on that homework assignment? I will point out for those of you who didn't stick around for the practicum session on Wednesday last week, we basically did something very similar to problem 2. We worked that out in the practicum session, so you can check the video on the YouTube channel for that. So any questions on homework 8? All right, so tonight our main purpose is essentially an exam 2 review. I don't have any formal review planned. I don't have any problems or anything like that that I intend to that I've planned to work out. Mostly, our review sessions are motivated by questions you have, since you are the ones who are here and connected in. So you should derive the benefit from it. So if there are any particular questions, anything at all in method of joints, method of sections, or frames, any particular problems that gave you trouble that you want to take a closer look at, now would be a good time to ask. Might also not be a bad idea to take a look through the old exam too and see if there's anything on there that seems a little bit challenging to you that you'd like to go over. Does anyone have any suggested topics to take a look at? Any problems that gave you issues?
I see problem 2 on the exam.
Problem 2 on the old exam too?
Yep.
All right. So Nang's the first out of the gate with this. Let me pull that up here. All right. So let's see here. Whoops. There we are. All right. So problem 2. This is a method of sections problem. Tells us to use the method of sections to find the loads carried. Generally, it's a good idea to follow what is suggested in the problem. If the problem says use method of joints, use method of joints. You're probably not going to do any better with it by trying to do method of sections, or trying to do method of joints in a method of sections problem. Here, this is a method of sections problem. They want you to find the loads carried by the specified members, in this case CD, CG, and HG. It's not a bad idea to make a little mark through those, CD, CG, and HG, and figure out whether they're in tension or compression. So find out the load. We have something very specific here. Tells us to state our answers to 3 significant figures. So right away, that's a clue as to how many digits to round off to in our normal calculations. So as we're doing our calculations, we're going to want to keep 2 sig figs more than what we need in the end. So we'll keep 5 sig figs through the problem. So that's the problem to work with. Now, as you're aware of at this point, I like to throw in problems that look a little bit different, but that are treated by the same exact methods that we're already familiar with. The thing that looks a little bit different here, something we really haven't seen before, is that apparently the supports are on different levels. And that's okay. I mean, we could have a kind of a step or something like that here that this is on. That doesn't really change how we do the analysis of the problem. We can assume those supports are sitting on some sort of ground level or some sort of ground support. Doesn't change anything about how we do the problem. So let's go ahead and start with the external problem. We need to find our reaction forces at A and G. So we'll start that with a free body diagram. So free body diagram, it's going to look something like this. Scale might not be quite right, but it's close enough to get the point across. There we go. So we've got joint A down here, then we've got B, C, D, and E, G, and H. We've got a pinned support down here at A. So that means we're going to replace it with 2 forces, RAY and RAX. G is a roller support, so we're going to replace that with a single vertical support, RGY. Then we've got these other external forces. We've got 5 kips over there. We've got 15 kips here. And we've got 20 kips there. No other forces involved. We had a 10-foot distance here. This whole thing overall is 12 feet. And then each bay is 20 feet. So yeah, the scale is a little bit off, but we'll figure it out here. So we start out our external problem with our sums of forces in the x direction. So we take our sum of forces in the x direction, and the only force we've got in the x direction is RAX. So that's equal to 0. So we automatically know RAX isn't there. Sum of forces in the y direction, we've got a positive RAY, we've got a positive RGY, and then we've got all these forces pushing down. We've got a negative 20, negative 15, and negative 5. So that's got to be equal to 0 if this whole thing's in equilibrium. So if we simplify that down a little bit, we've got RAY plus RGY minus 20 minus 15 is a negative 35, minus 5 is a negative 40. So we have RAY plus RGY is negative 40. And then we need moments, and we need to pick a pivot point. And seems to me that our traditional pivot point here, picking point A, ought to work with no problem. So we'll pick A as our pivot point. That means RAY will not have a moment, but all the other forces that are still there will. RGY, the 5 kip, the 15 kip, and the 20 kip force. All of those have an arm, the distance between the pivot point and the line of action of the force. So working our way left to right here, let's take that 20 kip force first. That 20 kips is 20 feet away. So we have 20 times 20. If we're pinned at A and pushing down at C, that'll cause a clockwise rotation. And from our coordinate system, counterclockwise moments are positive, so clockwise moments are negative. We've got our 15 kip force. That's 40 feet away. It's 2 bays away. So we've got 40 times 15. Pushing down at D, that's still going to cause a clockwise rotation about A. So that's negative. We've got 5 kips 60 feet away. And that's also going to be negative. Pushing down at E will cause a clockwise rotation. There we go. And RGY, that is 2 bays away, so that's 40-foot arm. RGY is our force, so we've got 40 RGY, and if we're pushing up at G, that'll cause a counterclockwise rotation, and counterclockwise rotations are positive. So there's our moment equation. So 4 terms in the moment equations, we had 4 forces that were that created moments. So we can simplify these down a little bit. Negative 20 times 20 is a negative 400. We have negative 40 times 15, which should give us a negative 600. We have negative 60 times 5, that should give us a negative 300, plus 40 RGY. If we combine together our numbers, so we've got our 400, negative 600, and the 300. There we've got a negative 1,300 plus 40 RGY equals 0. Add 1,300 to both sides, and we have 40 RGY equals 1,300. divide both sides by 40, and RGY equals 32.5. And since all of our forces were in units of kips, we have 32.5 kips. So that's what RGY is pushing up with. Seems reasonable. It's on the same kind of order as our applied forces, 20 kips, 15 kips. We've got 40 kips pushing down, plus we've got, so it makes sense we'd have something around that pushing back up, since most of them are concentrated pretty close to where G is. To figure out A, we can go back into our y direction equation. We have RAY plus 32.5 minus 40 equals 0. So that will tell us that RAY must equal 7.5 kips. Since RAY plus RGY, the forces pushing up, need to equal the forces pushing down. So 32.5 kips plus that 7.5 kips gives us the 40 that we need. So those are our reactions. So that's the external problem, first step in doing the method of sections. If we go back over to the picture, we have to decide now that we know our reaction forces, we have to decide how we're going to close this loop. We're going to be able to cut through all three members that we want in one pass, in one cut. But we've got to close that cut either to the right or to the left. And either way can work. Either way is fine. Either way should give you the same answer. If you do all the math right, it has to give you the same answer. It can't depend on how you solve the problem. If we close to the right, we're going to be dealing with this 15 kip force, the 5 kip force, and RGY. If we close off to the left, we're only dealing with two forces, the 20 kip force and RAY. So closing off to the left seems to be a little bit easier here. Just a little bit, it's marginal. So that little section of the truss that we're cutting out is going to look something like this. If we draw a picture of the part inside, we've got that section from A to B. We've got A to H. We've got B to C. And we've got C to H. And that's where we make our cut. So we've cut right here in member CD. And that'll expose the force FCD. We are cutting through CG. So that'll expose the force applied to member CG by the part of the truss we've cut away. Call that FCG. And then we've got where we cut through HG, GH, FGH. We're going to need an angle. We need that angle there. But fortunately, that's not too hard to find. If we go back up to our picture, each of these triangles is 10 feet high and 20 feet wide. So since we're looking for this angle right here, opposite over adjacent, we do inverse tangent of 10 over 20, opposite over adjacent. So we do inverse tangent, and we get 26.565 degrees. So that's the angle there, 26.565 degrees. One of the recurring problems I've seen in looking at the homework is people messing up sine and cosine when you're looking at opposite and adjacent. Make sure you're looking at that carefully. If you decided you wanted to work with this angle down here, that's fine. But you're going to get the complement to 26.565. You'll get 63.435. And it's fine to work with that. Just be aware that when you want your y components, you're going to need to use cosine, because the cosine goes with the adjacent side, and the adjacent side to that 63.435 angle is the y side. Here, my adjacent is x. So x is going to go with cosine if I use 26.565. So make sure you're looking at the angle you're using and what is opposite and what is adjacent. We've got our force here also. We've got that 7.5 kips right there at A. So there's our free body diagram of the part of the truss isolated by our bubble. Don't forget the 20 kip force here. Always a good idea to go back before you do your analysis and make sure you've caught all the forces. So I've got that 20 kip force at C. I've got the 7.5 kip force at A, my reaction. No RAX because there were no side loads. And I've got my 3 unknown forces. So it looks like we're good to go. So let's do our sum of forces in the x direction. In the x direction, we've got all of FCD to the right, and to the right is positive, up is positive, and counterclockwise moments are positive. So we have positive FCD. We've got all of FGH, and we've got a piece of FCG. Now, since I've decided I'm going to use this 26.565 degree angle, and the x component is adjacent to that, adjacent's going to go with cosine. So I'll have FCG cosine 26.565 degrees. And that's pulling to the right, the x component's to the right, so it's positive. No other x components involved, so that's all we've got for our x component equation. For the y direction, we've got a positive 7.5 kips from our reaction at A. We've got a negative 20 kips from the applied load at C. And then we've got the piece of FCG pulling down. And since that's the opposite side, that's going to go with sine. And since it's down, it's going to be negative. So negative FCG sine 26.565 degrees. That's all I've got in the y direction. And then we've got our pivot point. We've got to do our sum of moments about a point. And the easiest point to pick in this case is going to be point C, because it's going to knock out FCG specifically, because that one's the one that's got a hard moment to figure out about any of the other points. Point C is about the only place where we've got a nice simple moment for FCG, that moment being 0. It'll also knock out FCD and that 20 kip force. The only forces that will have moments will be FGH and the 7.5 kip force. So if we use joint C as our pivot point, FGH has an arm. According to our drawing, if we go back to that, FGH is down here, the pivot point's there, the line of action's down here, the arm is that distance between the pivot point and the line of action of the force. That's 10 feet. So we have 10 FGH. If we're pinned at C and we pull to the right at H, that's a counterclockwise moment, so that's positive. Then we've got joint A, which is at 7.5 kips. Joint A has an arm that is 20 feet away from C. If we go back to the picture, we can see that here. Right here is A. The line of action of A is right there. Pivot point's right here. I'm still seeing a little bit of confusion with that, with some of the forces. So if you got that wrong on your homework, got something wrong with an arm, make sure you're paying very close attention to that. It's an easy way to make a small mistake that just messes up the whole problem. So got to get those arms right. Each bay is 20 feet wide. So A, the line of action of A is 20 feet away from C. So we've got 20 times 7.5. And if we're pinned at C and we push up at A, that'd be a clockwise rotation, so negative. Now, as it usually works out, the moment equation's easy to solve. We've got 20 times 7.5. That'll be 150. So we get 10 FGH minus 150 equals 0. Add 150 to both sides, and we have 10 FGH is 150. Divide both sides by 10, and FGH is 15. So member GH came out to be 15 kips and came out positive, which means our assumed direction is correct. The rest of the truss really does pull on member GH. That means it's putting member GH into tension. So if we go back to the chart, we can fill that in. We know we're in tension, and we've got 15 kips. Now, we can be careful here because that's the final answer. For that, we need that to 3 sig figs. To make a 15 into 3 sig figs, we do 15.0. It's kind of picky to do that with that because we really haven't done any round off at all. This is actually an exact answer up to this point in there, but to meet the objective of the problem, we'd write it as 15.0 kips. And be careful, and the ones we write up on our own, I usually put the units up in the header of the table. That's not there, so make sure you put the units in or make a note somewhere, cross that out, and write loads and kips or whatever you need to do to communicate the right units. So if you just leave it blank, I'm going to take off points. So 15.0 kips in tension. So we got 15 kips there for GH. We go up to the y direction equation. We can solve that. We can simplify it a little bit here first. 7.5 minus 20. We've got negative 12.5 minus FCG sine of 26.565 degrees. That's equal to 0. If we add 12.5 to both sides, we'll get negative FCG times the sine. Is that positive 12.5? Then we divide both sides by negative sine of 26.565 degrees. The negative will cancel out the negative sign there, giving us a positive FCG. That's what we're always solving for. And the signs will cancel each other out. So be careful to watch those SIGN signs, because those can cause problems for you too. So we have negative sine of 26.565. That's what we divided by. Just like any other time we divide by a coefficient, we always divide by the coefficient including its SIGN sign, its algebraic sign. So we got 12.5 divided by a negative sine of 26.565. And that gives us a negative 27.951. So FCG is a negative 27.951. And that's also kips. And just double checking that, make sure I didn't key something in wrong there. Oh, looks fine. So negative 27.950. So two things about that. First, it's negative. So that means that member CG is not pulled on by the rest of the truss. It's pushed on by the rest of the truss. Member CG is in compression. Now, that being said, when you look at filling in your table, we never put negative values in that load column. The load is an absolute quantity. It's how much load is there. We use up any negative signs there are when we interpret tension or compression. So that it's negative tells us that member CG is in compression. Remember, in method of sections, as long as you set it up the way that I've shown you, if the answer comes out positive, it's tension. And if it comes out negative, it's compression. So tension and compression are as simple as interpreting the sign when you are working with method of sections. We all know method of joints is a little more tricky. We can fill in the table here, and we can go ahead and round. As long as we don't use the rounded value in our final calculation here, we can go ahead and round this to 3 sig figs. And to 3 sig figs, this would be 28.0. So 28.0 kips filled into the table. So finally, we can go and do our x direction equation. We can fill in what we know, including the signs. The value of FCG, that symbol, is a negative number. You have to plug that in to the equation, including the sign. We can interpret the sign away when we fill out the table, but when we're solving equations, we've got to include that sign. We can't just drop it. So let's fill in what we know here. We don't know FCD. FGH is a positive 15 kips. FCG is a negative 27.951. Cosine 26.565 degrees. If we take 27.951 times the cosine of 26.565, we've got 25. So this is FCD plus 15 minus 25.000. 15 minus 25 is a negative 10. So we have FCD minus 10.000 equals 0. So if something minus 10.000 is 0, then that something must be 10.000. So FCD is a positive 10.000 kips. So that means that member CD is in tension. So let's go over to the table here. Member CD, we can fill that in now, rounded to 3 sig figs. And that came in tension.
Is it acceptable if we just write kips over top of load?
Yeah, anything that clearly communicates what your units are is fine by me.
Okay, just making sure.
About the only time I end up taking off points for units is when they're just not there at all, where there's just no indication of it. I even get pretty lenient on it when it's shown in the work, but you didn't put it in your final answer. As long as I could see it in the work, at least tells me you knew it at some point. But if they're just completely gone, then I can't do anything with that.
Understood.
But as long as it's clearly communicated.
So for our loads, we should always keep it positive, right? As long as we indicate which is tension and compression.
Yep, the sign factors into tension and compression. The load is an absolute quantity. It's considered a magnitude. So in a sense, you could think about this as a vector representation, where compression or tension is telling you about direction, and the load is the magnitude. So the magnitudes of vectors are always positive.
Okay.
Makes sense there?
Yep.
All right, any questions on that one? Now this one's got kind of a complex load on it. To be able to get essentially both the top and bottom to be in tension like that, CD and GH. You've got some load over here that's trying to bend the part of the truss here between A and G, trying to bend that down. So that's going to stretch out GH, but it would tend to put CD into compression. But then you've got this 5 kip load over here, which is trying to bend everything this way, trying to stretch out the top. And it's far enough away that it can actually win and be able to turn that top from compression to tension, but not really have an effect on what's going on down here. So this isn't a pure bending state. in a pure bending state, you'd either have just tension on the top and just compression on the bottom, or vice versa. Here we've got something that's kind of twisted around, where it's got some bending in one direction on one part, so it's kind of bending like this over here, but it's bending like this over here. It's kind of a strange load on the system, so it's not the easiest one to try to just guess the tension and compression status on. All right, any other questions on the on exam 2? Let's see.
So is
Pretty
that typical for the exam to have just the 3 questions?
Yeah. Sometimes I've gone with 4, where I've done kind of a method of joints, method of sections, frames, and then kind of like student's choice. So here's a truss, do it however you need to. But that's been pretty rare. So I think 3 is pretty standard here, and you can expect the lines that they're going to go along. Method of joints, a method of sections, and a frame problem.
Do you think it's beneficial for us to just go over all 3 then?
It's probably not a bad idea if you've got questions on them. I mean, if everyone here is feeling perfectly fine with method of joints, you know, this one is a typical 3-member method of joints problem. And about the only thing I think that would immediately trip people up, or that I'd expect to see errors on, would be people forgetting about this 57-pound force in their moment equation. So they're used to thinking about those gravity loads, but those side loads, like this could be a wind load or something like that on a roof truss. I mean, I could certainly do them. I'll run them through if you want. But if everyone's feeling perfectly comfortable with something, I'd rather spend time on things that you're not feeling as comfortable with. But if no one has any other suggestions, I'd be fine with that. Going
I'm
once.
good with whatever.
All right.
Hey, Tom,
Yeah, go ahead.
I don't have it in front of me. What's the third one?
The third one is a frame problem. It's a gantry crane.
All right, I have problems with those. So
Okay.
after Mark's number.
Yeah,
one, we
let's
can do
let's
this.
just run it.
Go with that.
All right. So let's go here for, let me scrap my my pages here and get to some fresh scrap paper. There we go. All right. So here we've got problem number 1, which, by the way, you can probably expect pretty reasonably equal distribution of points on the exam. If there are 3 questions, chances are I'd probably go 40, 40, and 30. I'd probably weight the method of joints and method of sections heavier because those are really the most important concepts to be getting out of the class. The frame would probably be weighted a little bit lighter. That'd be my first instinct on it. So somewhere in that neighborhood, 40 points for each of those. I forget what it is. You can check in the solutions, as those are posted for exam 2, for the old exam 2, and see what my point breakdown was. But that'd be pretty typical, at least from what I normally would do. So let's take a look at this one here. We've got a 3-member truss. It says to use the method of joints, which you really don't have a lot of choice of. Try doing method of sections on one of these sometime, on the 3-member truss, and you'll see pretty quickly why you don't end up doing method of sections on these, because it breaks down into method of joints. When you can't cut through 3 members in one cut, you're just doing method of joints. So you end up with basically the same problem. So we may as well use the method of joints on this. Determine whether each member is in tension or compression, and state answers to 3 sig figs. So same procedure as with method of sections. First, we've got to do the external problem. So let's sketch our free body diagram. So up here at joint B, we've got a 57-pound force and a 100-pound force. 57-pound force to the right and a 100-pound force down. Joint A is a pinned support. So we can replace that with two forces, RAX and RAY. And then over here at joint C, we've got a roller. So vertical RCY. To the right is positive, up is positive, and counterclockwise moments are positive. So we'll do our sum of forces in the x direction. We've got a positive RAX by assumption, and then we've got a positive 57-pound force. That's given to us. No other x direction forces, so that lets us make a solution right away. RAX is negative 57 pounds. So that means I guessed the wrong direction down here. I assumed RAX was to the right, but it's got to be to the left, which makes sense. We've got a force pushing to the right, so there's got to be something going to the left to counteract it. And we'll correct that when we draw our next free body diagram. We'll do our sum of forces in the y direction. We've got a positive RAY, a positive RCY, and a negative 100. The best we can do with that is just add 100 to both sides and get the same y equation we normally get, which says that the two unknown forces pushing up had better total up to be the total forces pushing down. But we can't solve that yet, too many unknowns. So then we'll take our sum of moments and we'll pick A as our pivot point. Sum of moments about A. RAX and RAY will not have a moment because they're both pushing on A. But RCY will have a moment. The 100-pound force will have a moment. And that 57-pound force, that troublemaker 57-pound force, will also have a moment. Anything that's got a line of action that doesn't pass through A, that's going to have a moment. So we're going to have three terms in our moment equation. Now, RCY, according to the drawing, is 17 feet away. So it's 17, I'll drop the units for now. 17 feet away times RCY. If we're pinned at A and pushing up at C, we've got a counterclockwise moment. So counterclockwise moments are positive. So we've got positive 17 RCY. We've got that 100-pound force, and that line of action for that 100-pound force is straight down. The distance between the pivot point and the line of action, according to our drawing, is 6 feet. So we've got 6 times 100. If we're pinned at A and pushing down at B, that's a clockwise moment, so that's negative. And then we've got 57 pounds. The line of action for that is above A, and that's a height of 8 feet. So we've got 8 times 57. If we're pinned at A and pushing to the right at B, that's a clockwise moment, so it's negative. If we clean up the numbers a little bit, we've got 17 RCY minus 600 minus 8 times 57. So that's a negative 456. Combining that together, we've got 17 RCY minus 1056. That equals 0. If we add 1056 to both sides, we have 17 RCY. It's 1056. Divide both sides by 17. And we get RCY is 62.118. And the units here are pounds. So we've got 62.118 pounds pushing up at C to support this structure. Knowing that, we can go over to our y direction equation. We've got RAY plus 62.118 is equal to 100. Subtract 62.118 from both sides. We've got 100 minus 62.118. And that gives us 37.882. So RAY 37.882, also pounds. So there we've got our reactions nailed down. Got to make sure to translate all of them over. Don't ignore that X direction. Another very common mistake I see people make is they get so used to doing problems that just have gravity loads in them that they completely forget about RAX and drop it out of the problem. That's going to mess things up. So we've got to have all three of those reaction forces carried over into our intermediate free body diagram. So I think I'm going to draw that right here. So we've got something that looks sort of like this. We've got 62.118 pounds pushing up at C. At A, we've got 37.882 pounds pushing up, but then we have 57 pounds pulling to the left at A. Then we have it's at B, 57 pounds to the right and 100 pounds down. That's a joint B. So there's our intermediate free body diagram. So we've got the external problem solved. The answers seem reasonable. We're pushing down with 100 pounds of force, so that 100 pounds of force is going to get distributed. Normally, we'd expect the support closer to the load to bear more of that load, but this side load is trying to pick up A. So it's loading down C more than we would normally expect. It's making C dive down while A tries to pick up. So it shifts the load. In fact, we do this kind of thing all the time where we use forces in kind of strange directions to shift a load. Those of you who might be a little more familiar with towing vehicles, things like that, you might have heard of something called a weight distribution hitch. The weight distribution hitch works in a very similar way to this kind of thing, where we're using a side load to shift essentially how that tongue load is balanced out on the vehicle to help balance things out a little bit. So let's go into the method of joints here. Almost always a good idea in these kinds of problems to work on these support joints, mostly because we've got this unknown that's horizontal. Working with unknowns at angles means we're taking sines and cosines of unknowns, and that makes the algebra a little more complex. Having one of those is bad enough. We want to avoid, if we possibly can, working on a joint where we have two unknowns with angles involved, because we'd be taking sines and cosines of different angles, and that's just ugly. In 2 dimensions, we should always be able to find, unless I were to go and create some really nasty structure, we should always be able to find some joints that are easier to work than others. So it's up to us here whether we work at joint A or joint C. If you remember the rule that I gave you a little earlier, it said that when you're working with a method of joints problem, you're always going to have to solve one fewer joint than the number you've got. Here we've got 3 joints. I'm going to have to work with 2 of them. And so I don't want to work with B, so that means I'm going to work A and C. So just out of habit, I'm going to work A first. C might be a little bit easier, but just because it lacks that other side force. But since we have to work both of them anyway, we may as well. So let's go over to joint A. So we're going to draw the free body diagram at joint A to make sure that I don't make a stupid mistake and ignore a force. I'm going to draw my little bubble around A and make sure I count up how many forces are acting there. I've got 4 forces. I've got the 2 reaction forces, and I've got these 2 unknown forces. So I should have 4 forces in my free body diagram. And I always like to draw the forces as if they're pulling. So rather than pushing up with this 37.882 pounds of force, I'm going to pull up with 37.882. I always draw my known forces in first. That makes it a little easier to figure out reasonable directions to draw my unknown forces. So those are my 2 known forces. Then I've got to fill in values for this unknown force on the joint due to member AB and the unknown force on the joint due to member AC. Now it makes sense here to draw the force due to AC pulling to the right. It's just easier to draw that way rather than drawing it on top of the 57-pound force and run the risk of losing it. When you've got two arrows drawn on top of each other, they often start to look like one arrow, and then you make mistakes pretty easily. That also gives me a better idea of where to put AB. If I drew AB pulling up and to the right, that wouldn't be reasonable because there'd be no forces down. And to be in equilibrium, for every force to the right, there's got to be a force to the left. For every force up, there's got to be a force down. So here we've got member AB's force. I'm going to draw that as down and to the left. And that should be, I've drawn it kind of not quite at the right angle here, but I've got the down to the left going here. We need the angle. And you got to be careful with these angles. Sometimes it'll help to go back to the drawing, maybe even back to your original drawing, and sketch out what those angles are. There's the extended line for member AB and for member AC. That angle right there, the one to horizontal, is the one that I want. Fortunately, those two angles are the same. We call them vertical angles when they are across the X that way, and they are across an X. That is, those two angles have to be equal. Well, we can get that angle pretty easily from this triangle. We've got 6 feet there, we've got 8 feet there. So our angle is going to be the inverse tangent of opposite over adjacent, 8/6. There have been several times in a lot of the homework assignments and such that I saw people submit in quizzes where people have gotten the complement. They've gotten the angle on the other side, gotten the angle to vertical. And that'll work as long as you use it in the right place. But what I most often see is the angle drawn to horizontal, but the angle calculated to vertical. That's usually flipping over the order here. So pick the angle you're working with. Opposite over adjacent will give you the angle. So inverse tangent, that's 53.130. So that's my angle here, 53.130 degrees. So there's my free body diagram for joint A. And of course, remember our directions. To the right is positive, up is positive. And we don't need moments here because none of these forces have a moment. This is a concurrent force system. All the forces push or pull on a single point. So we're only going to get two equations: the sum of forces in the x direction and the sum of forces in the y direction. If we take our sum of forces in the x direction, we've got FAC to the right, so that's positive. We've got that 57 to the left, and then we catch a piece of FAB. We catch the adjacent piece, the part next to the angle. Adjacent goes with cosine, and that's pulling to the left, so it's negative FAB cosine of 53.130 degrees. And then we can do our sum of forces in the y direction. We've got a positive 37.882 pounds. And then we've got the downward piece of FAB. Well, that's the opposite side. Opposite goes with sine. So we have minus FAB sine of 53.130 degrees. So there we go, our two equations at joint A. We can solve the y direction equation right away. If we subtract that 37.882 from both sides, we have negative FAB sine of 53.130 degrees. That equals negative 37.882. And then remember, when you divide by a negative number, you've got it. When you divide, you've got a negative coefficient, you divide by that negative to cancel that out. So we have divide by negative sine of 53.130. The negatives cancel each other out, giving us a positive FAB, and the signs cancel each other out on the left. So we get FAB equals also positive, so we know something about our answer already. FAB came out positive, so our direction is correct. Our assumed direction is right in the free body diagram. The value, we get 37.882 divided by the sine of 53.130, and that's 47.353. So 47.353 pounds. So it came out positive. So that means that our assumed direction is correct. We have to interpret that. Knowing the direction is correct now, we have to interpret whether that is tension or compression. And if we compare back to our original drawing, joint A is right there. Member AB is up and to the right, but it's pushing joint A down and to the left. So member A is up here. So kind of shown in hidden lines. Member AB is up there, but it's pushing joint A away. So we have to answer whether that's tension or compression. Remember here we're looking at the joints. If a member is in tension, then it's been stretched out, and its tendency is to try to shrink back to its original size. A member in tension tends to pull the joints inward. That's what tension looked like. From the point of view of the joint feels pulled inward when the member is in tension. If a member is in compression, then it's been squeezed down, and its tendency is to try to expand back out. So it pushes the joints away from the middle. That's compression. Now, if that feels opposite to what you expected from method of sections, it should feel opposite because we are actually looking at the opposite force, as in the equal and opposite force. Good old Newton's third law. So we are looking at the reaction to the force on member AB. The force on member AB is tension. We're feeling there is, is compression. We're seeing the reaction to that, which points outward. So outward is compression, inward is tension. The member trying to expand back to its original size drives joint A away. So member AB carries 47.353 pounds in compression. So we can go over to our table and tabulate that answer. We can round it off to 3 sig figs, so that'd be 47.4. We're not going to use the rounded number in the calculations anymore, but 47.353 pounds. And we've decided that's in compression. And it kind of makes sense that it's in compression. You've got a pretty good load pushing down here at the top. That's going to tend to squeeze member AB. The force, that 57-pound force, is going to try to stretch out AB, but it's not big enough, nor at a strong enough angle to really help out and counteract the effect of that 100-pound force. The tension or the compression here is less than we'd see it without that 57-pound force. Now that we know member AB, we can go and solve the x direction equation. We've got FAC minus 57 minus 47.353 cosine of 53.130 degrees. If we take that 47.353 and multiply it by the cosine of 53.130, we get 28.412. So we have FAC minus 57 minus 28.412 equals 0. Combine that 57 in there, and we get FAC minus 85.412 equals 0. So there, FAC is 85.412 pounds. The answer came out positive. So that tells us our assumed direction is correct. And if we go back to our drawing, member AC is to the right. So sketch that on top of the free body diagram, also in hidden lines. And it becomes clear that joint A is feeling pulled by member AC. When the joint is pulled by the member, that's tension. Looks just like what's going on over there. So member AC is in tension. So it carries 85.4 pounds in tension. Now we've learned everything we can from joint A. We've solved for all the unknowns, member AB and member AC. We need to figure out member BC, and the only way to do that is to go over to joint C or joint B. Joint B looks ugly, so joint C looks like it'll be a little easier to work with. So let's go over to joint C, but don't let that work from joint A get too far away. So let's go over to joint C. At joint C, we've got one known force. We've got our reaction at C, which was 62.118 pounds. We also have a known force. So here's joint C. Draw our bubble around there. We're going to expect 3 forces in our free body diagram, but we already know what's going on with member AC. Member AC is in tension. So it's the stretched out spring that's trying to return to its original size. So it's pulling joint A that way. It's going to pull joint C that way. So the load carried by member AC is going to pull joint C to the left. And it's going to pull joint C to the left with 85.412 pounds of force. Don't make the mistake of going back to your table and reading out 85.4 pounds. That's been rounded to 3 sig figs. If we want our answer here for BC to be good to 5 sig figs, we can't use a rounded off value to it's already rounded to 3 sig figs. So go to your full precision value, 85.412. So member AC pulls to the left with 85.412 pounds of force. And then we've got member BC. Now it's pretty obvious from the directions involved here that the only way that it could make sense is to have joint C be pushed down and to the right. That's the only thing that looks like a tug of war, no one wins. So that's FBC. Now we're going to need an angle, and I generally go for the angles to horizontal when we're trying to construct those. So draw that little cross here. That's the angle I'm looking for. It's the same as this angle right here. That angle is formed from a triangle that is 8 feet high and 11 feet on its base. So the angle is going to be the inverse tangent of opposite over adjacent, 8 over 11. So there we get 21.819 degrees. Okay, I keyed something wrong there. Not sure what I did, but that number didn't sound right to me. So 8 divided by 11, third try here, make sure we get the right value now. 36.027. That sounds a little bit better. What did I do? Key in 6. Yeah, that's what I did. I keyed in 6 instead of 8. This is 8 feet tall. So 36.027 degrees. Kind of crammed in there. All right, so we've got a non-concurrent force system. Sorry, a concurrent force system. So all we've got are 2 equations, the sum of forces in the x direction and the sum of forces in the y direction. We're only going to need one of those because we've got a sum, or we've got only one unknown. I'm going to go with the y direction equation here because maybe I messed up and got the wrong value for member AC. But if I feel pretty confident about that 62.118, that came from my external problem. Didn't rely on any other calculations I did. So it's closer to the original information in the problem. It's a little more precise. It's not going to matter to 3 sig figs, but as long as I did my math correctly over here. But if I made a mistake over here in figuring out AC, I can insulate myself a little bit from that by working with information that doesn't depend on it. In either case, if you've done your math correctly, you should end up with the right answer. So kind of by definition. So sum of forces in the y direction, we've got 62.118 up, and then we've got the vertical piece of FBC. That's the opposite side, so it's going to go with sine of minus FBC sine of 36.027 degrees. If we subtract 62.118 from both sides, I have negative FBC sine 36.027 degrees. That equals a negative 62.118. Divide both sides by negative sine of 36.027 degrees. And we'll get, let's see, 62.118, 36.027 sine, divide, and we get FBC is a positive 105.61 pounds. So 105.61 pounds. Came out positive, so our assumed direction is correct. And if we look at the original drawing, there's joint C. The member is up and to the left. So the member in the problem is right there. Joint C is being pushed away. That's compression. So we have 105.61, or rounded to 3 sig figs, 106 pounds in compression. And if we look at the drawing, it kind of makes sense that it's in compression. Normally, that 100-pound force alone would put both AB and BC into compression. The 57-pound side load here at B tries to stretch out and relieves a little bit of the compression in AB, but it adds to the compression in BC. So it's shifting that load. That's how we end up with more load on joint C. It shifts some of the stress that's being carried by AB into BC. It makes AB less loaded while BC is more loaded. And there we go. 3 sig figs, units are there. Pretty confident in the tension and compression. Any questions on that one? All right then. Well, let's wrap it up here with problem 3, where we're looking for the magnitudes of the forces at joints C, D, and E. And I kind of threw some goofy stuff into this one. This is supposed to be a roller support. For some reason in the drawing, I couldn't get it to actually show up as a circle. So it's assumed to be a roller. That's not really the goofy thing here. The goofy thing is this distance right here, pi feet. It turns out you're not going to actually need this distance, so it doesn't really change anything, but I just kind of threw that in there. Not too many people ever call me out on that one either. But if we look at the structure here, we've got a pin support at A, got that roller at B, and then we've got a 5,000 pound load, 5 kip load, hanging out here at the end. And we want to know what kind of stresses are on these 3 pins holding this structure together. Now, in order to figure it out, we've actually got to find more than just those 3 pins. We're going to have to find out about our reactions up here too. But in order to have the right number of equations, we've got to have a number of equations consistent with our unknowns. The x and y components here of the forces at the pins are our unknowns. We've got 6 missing pieces of information. The magnitude, remember, isn't an unknown, because once we know x and y, the magnitude is just x, the square root of x squared plus y squared. So it doesn't count as an unknown. So we've got 6 unknowns there, and we need 3 equations for that. And if we set it up right, we might be able to get away without it, but get away without finding the supports here. But that would mean we'd have to work with this slanted member. And as I've advised in the past, working with slanted members is usually kind of a pain. I'd prefer to work with horizontal and vertical members. Those almost always end up with easier equations to solve. But to work with this vertical member here, I'm going to have to know what's going on at A and B. So I really need to figure out A and B also. So let's first do the external problem on this one. So in doing the external problem, we need a free body diagram. And the free body diagram is going to look pretty close to the overall structure. We've got our 2 main members in this cross member. We've got our 5 kip force pulling down here. We've got this roller at B. And remember that the free body diagram removes the supports and replaces them with the forces that are supplied by those supports. I'm going to assume the reaction at B in the x direction is to the right. Kind of makes sense, because if I pull down here, this thing's going to want to go to the left to fight it, to keep it from going to the left. I've got to push something to the right. Down here at the bottom at A, we had a pin, and pinned supports always have 2 reactions, RAX and RAY. There are no other forces involved in the problem. We've really only got 4 forces acting on the whole structure: the reaction support forces, or the support forces at the reactions at the supports, and this applied 5 kips. So let's do our sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. In the x direction, we've got a positive RBX and a positive RAX. Nothing else. In the y direction, we've got a positive RAY and a negative 5 kips. Well, that is something we can solve right away. RAY is 5 kips. So RAY does push up with 5 kips of force to counteract the 5 kips down. So RAY is 5 kips. And then we need our pivot point. We need a moment about the pivot point. I'll pick joint A for that. So we'll do our sum of moments about joint A. That's going to knock out RAX and RAY, but RBX is going to have a moment, and the 5 kip force is going to have a moment. For RBX, we need an arm. We need the distance from the pivot point to RBX. And if we go back to our original drawing here, we've got 6 feet plus 8 feet plus 2 feet. 2 plus 8 is 10, plus another 6, 16. And if we're pinned at A and pushing to the right at B, that's clockwise rotation. Clockwise rotations are negative. And then we've got our 5 kip force. We're going to need an arm for that. The 5 kip force is down here. That's its line of action. The arm is that perpendicular distance. And according to the drawing, that distance is 6 feet plus 3 feet. That's 9 feet. So we have 9 times 5. If we're pinned at A and pulling down at F, it's counterclockwise rotation. So it's positive. So we can clean that up a little bit. We've got negative 16 RBX plus 45 equals 0. Subtract 45 from both sides. Would help if I was on the screen. There we go. So subtract 45 from both sides. Divide both sides by negative 16. And we get 2.8125. And this one's in kips. So RBX came out positive, so we know our direction's right, and it's value 2.8125 kips. We can go to the x direction equation and figure out our AX now. Our BX is 2.8125 plus RAX equals 0. If we subtract 2.8125 from both sides, we have RAX is negative 2.8125 kips. So RAX came out negative, which means our assumed direction is wrong. RAX has to be to the left, not to the right. So there's our external problem. So we could go back to our original picture here and kind of sketch that in. Our BX was 2.8125 kips. Our AX was in the opposite direction, 2.8125 kips. And RAY was 5 kips up. So that'll help us out with our free body diagram for member AB. Now, to go any further, to figure out what's going on at these 3 internal joints in the problem, we have to blow the structure up. We have to separate it into not one structure with one free body diagram, but 3 members with 3 free body diagrams. Remember, we can only expose forces when we draw the free body diagram of something that force acts on. When we're dealing with the external problem, those forces at C, D, and E are internal forces. They're not external. These methods that we use to solve for equilibrium forces only works with external forces. So the only way to make an internal force into an external force is to break the structure apart. On paper, of course. It's the same thing we do in method of sections. When we cut through a member, we're turning an internal force into an external one so we can analyze it. So we need to blow this structure up a bit. And I've already decided I only want to work with the horizontal and vertical members. Those will give me enough information to fill in this table. So those are the only ones I'm going to draw. If you want to see drawing out all of them, we did a problem very similar to this when we first started frames. So I would go to the YouTube channel for that and take a look at those. But here we're only going to need the horizontal and vertical ones. So there's the vertical member, AB. We have a force over here at 2.8125 kips. We have a force over here, 2.8125 kips. We also have that force up of 5 kips. But now we've got two internal forces. When we break this structure out of the truss or out of the frame, we expose the forces at D and at C. Now both D and C are pins. And as a pin support, we have two reactions. Just like the pin support at A had two reactions. But we don't know anything about what those are, so we just have to guess. I'm going to call the two reaction forces here at D RDX and RDY. And I'm going to do the same thing over here at C. I'm going to say RCX and RCY. The first time I draw a free body diagram that involves a joint, the first time I use that joint, I always assume the directions to be positive. That's going to be important here later when we draw the free body diagram for member CF, because we've already made some assumptions about joint C. All right, so let's draw our free body diagram for member CF. So we'll draw that over here next to it. Separate structure, separate free body diagram, but nearby so that we can compare things. We've got that 5 kip force over here. We've got joint E and joint C. Now joint E I've never used before, so I'm going to assume positive directions here. FEX and FEY. But joint C, I've already made some assumptions about. Where these two frame members join together, we've got to have equal but opposite forces. The force that is experienced by member CF is going to be equal and opposite to the force experienced by member AB. That's the whole point behind equal and opposite forces. One body feels the opposite that the other body feels. And we have to take that into account in the free body diagram. So if I'm going to use these same symbols, which I have to, RCX and RCY, I've got to make the opposite assumptions. RCX is going to be to the left, and RCY is going to be down. That ensures that any equations that we get or any information we get from one free body diagram we'll be able to move over to the other without worrying about signs. We're taking care of the sign issues right here by making sure that the assumed directions for the forces are equal symbols, equal values, but opposite directions. That's the one trick in doing a frame problem and setting the problem up. You've got to make sure that at corresponding joints, you've assumed opposite directions for the forces. And that was joint F there.
Okay, I was just going to ask
Sorry,
you that.
yep.
It was throwing me right off.
Thanks, sorry about that. All right, so let's go ahead and figure these out here. Let's deal with the vertical member first. So the vertical member, try to keep this on the screen here. We've got sum of forces in the x direction. Well, we've got a plus 2.8125 kips and a negative 2.8125 kips. And you've all seen this. Those of you who have done the homework have seen that come up a couple of times. Those cancel each other out. So I'm not even going to bother writing them in my x direction equation, since I've got positive and negative of the same number. What I will have that sticks around is RDX positive and RCX positive. And to be in equilibrium, that sum has to be equal to 0. I've got my sum of forces in the y direction. I've got 5 kips. I've got to keep that one in there. There's no other 5 kips pushing down to oppose me. I've got a positive RDY and a positive RCY. And that equals 0.
Hey, Tom,
Yeah, go ahead.
I'm sorry. Before you go any further, how did those two cancel out? I'm missing something.
Okay. Let me go to a separate sheet here. So if we do our sum of forces in the x direction, we've got 2.8125. That's to the right. So that would go in positive 2.8125.
No, I understand that. I'm missing where we got um, the top one. What is that? On B?
Up here, this force, that was from the external problem. That was from here, where we had our free body diagram for the whole structure.
Oh, okay. Yep.
So that's
I
one of
got
the
it.
external forces. That was one of our reaction forces. That was the force from the roller.
All right.
All right.
Sorry.
No worries. So our y direction equation's there. Now we need our moment equation. It's always going to be best in these problems to pick one of your unknown joints. If you pick A, like we traditionally do, that's fine. It can work out, but you're only going to be knocking out forces you know, plus a couple forces you don't. You're still going to have two unknown forces with moments, and you can always find a pivot point in these kinds of problems. You can always find a pivot point where you'll knock out everything except one unknown force. So if I look at the drawing here, sometimes the drawing gives you some ideas about where to take those pivot points. I think I'm going to pick joint C for my pivot point on this one. So I'll take my sum of moments about joint C. If I'm pivoting at joint C, that's going to knock out RCX and RCY. It's also going to knock out RDY because RDY's line of action goes straight through C, no arm. It's also going to knock out this 5 kip force. Basically, any vertical force is knocked out, and any other force at joint C. So that means I'm going to have 3 forces in my moment, 3 terms in my moment equation. One from that 2.8125 kips up at the top, one from this 2.8125 kips down at the bottom, and then one from RDX. Those are the only 3 that I'm going to have a moment from. No moment from RDY or RCY or the 5 kips because those all shoot right through C, and RCX also goes through C. So 3 terms. The 2.8125 kips up at the top, according to the drawing, is 2 feet away. So I have 2 times 2.8125. If we're pinned at C and we push to the right at the top, that'd be a clockwise moment, and clockwise moments are negative. D is 8 feet below C. So the arm for RDX is 8. And if we're pinned at C and we push to the right at D, that'd be a clockwise moment. Clockwise moments are positive. And then way down at the bottom, we've got this 2.8125 kips at A to the left. That is, looks like 14 feet away, 8 feet plus 6 feet. So we've got 14 feet times 2.8125. And if we're pinned at C and we push to the left at A, that's a clockwise moment. Clockwise moments are negative. So there's our moment equation. So if we clean that up a little bit, negative 2 times 2.8125, and we've got negative 14 times 2.8125. That gives us a total of 45. So we have 45 plus 8RDX equals 0. Subtract 45 from both sides. We have 8RDX is negative 45. And divide both sides by 8. And RDX comes out to be a negative 5.625. So we can plug that into our table here, including the sign in this case. In this case, we're looking at components. And since in the end we're looking for magnitudes, we're not looking at the actual load. The magnitude is the load. So when we figure out that 5.625, 625 kips. We can go right to the table and plug that in. So that's our dx. We have negative 5.625 kips. So we've got something in the table. So we've got our RDX value. I'll try to leave that on here. There we go. Now that we know RDX, we can carry that up into our x direction equation. We've got negative 5.625 plus our cx equals 0. If we add 5.625 to both sides, we get our cx equals 5.625 kips. So we've got another one we can fill in. Our cx is 5.625 kips. And that kind of makes sense that those two should oppose each other. The 2.8125 and the other 2.8125, those cancel out. So the x direction forces here also have to cancel out. There are only two of them. So one's got to be equal and opposite to the other. And that works out. Unfortunately here, we can't do a whole heck of a lot with our y direction equation. That tends to happen when we have more unknowns than equations. This non-concurrent force system gave us 3 equations. But we've got 4 unknowns, our cx and y, our dx and y. But we ended up in basically the best possible situation where we got 2 numbers and an equation out of that. When you've got 4 unknowns, that's about the best you can hope for, is 2 numbers and 1 equation. We can clean the equation up just a little bit. We can say r dy plus r cy equals negative 5. But I'm going to take that, move that over here, put that in my equation bank, so that maybe later when I have some more information, I can use it.
Hey, Tom,
Yeah, go ahead.
how did you get a negative RDX?
Let's see here. Oh, look at that. Because I lost a sign, that's why.
Okay, I thought it was me, and I said,
Nope.
I don't know how we did it.
Nope, thank you. Because I was cheating on my calculator and I just ignored the signs and
Okay.
then put the wrong number in. Nope, very good, Mark. Thank you. This is a negative 45. Because negative 2 times 2.8 is negative something. Negative 14 times 2.8 is negative something. So adding those together should be a negative 45. So this should be positive. That should be positive. So this would be positive. All that would do is change this value.
Yeah.
And make that negative. And in fact, it will have no effect on our final answer because we'd be going for a magnitude
Doesn't
anyway,
matter.
and the signs won't matter. But it's not great practice. So thank you for catching me on that. I totally did that on purpose so you'd find it. But yeah.
Very sneaky.
That's correct. Yes, good. All right. Any other questions on the vertical member here? The rest of it should go relatively quickly. So let's take a look at the horizontal member. Now that horizontal member has 4 unknowns, but at the very least, we've got 1 additional piece of information. We're going to have 4 equations because we've got this extra equation I just put in my equation bank. And why we had to draw this equal and opposite is so that we'll be able to use this equation. If we didn't draw the arrows in opposite directions, then we'd have to worry about switching the signs around when we jump from one to the other, and that would be a big mess. So drawing corresponding joints with equal but opposite forces makes it easier to import information from one solution to another. So let's draw the equations for the horizontal member. We have our sum of forces in the x direction. We've got a positive REX and a negative RCX. Nothing else in the X direction. In the Y direction, we've got a positive REY, we've got a negative RCY, and we've got a negative 5 kips. Now, so far, neither of those are ones we can solve directly. Then we've got our moment equation. And again, good idea to pick a pivot point that's going to knock out things that you don't know. And here, the joint I know the least about is E. I do know some information about C. In fact, from our table, we already know what RCX is. So we've already got a piece of information we can use. I'd rather knock out things I don't know and make, hopefully, the solution for things I am trying to find a little simpler. If I pick E as my pivot point, it's going to knock out REX and REY. It's also going to knock out RCX since it shoots right through E. But RCY will have a moment, and the 5 kip force will have a moment. Now, according to our drawing, bring that back over here. The arm for, if we're using E as the pivot point, the arm for this 5 kip force is 3 feet. So we'll have 3 times 5. If we're pivoting at E and pulling down at F, that's counterclockwise moment. So that's positive. C is 6 feet away. So RCY's arm is 6 feet. If we're pinning at E and pulling down at C, that would be a clockwise moment, and clockwise moments are negative. So there's our moment equation. Not too bad. We've got 15 minus 6 RCY equals 0. If we subtract 15 from both sides, we'll have negative 6 RCY equals negative 15. And divide both sides by negative 6. And RCY is a positive 2.5. So there's another one we can fill into the table. RCY is 2.5 kips. Now, knowing RCY, we can figure out our EY, because we can go and plug that in. Our EY minus 2.5 minus 5 equals 0. So our EY minus 7.5 equals 0. And REY is 7.5. So we got a value for REY, positive 7.5. So we can fill in that in the table. Now for our top equation here, REX minus RCX equals 0, but we already know what RCX is. RCX is negative 5.625. Now be careful when plugging in negative numbers. Remember, you're just replacing the symbol. You've got minus whatever the value of RCX is. The value of RCX is negative 5.625. So here you're subtracting a negative. Remember that old keep, change rule. It's the same as adding. So REX, if you work through the algebra on that, subtract the 5.625 from both sides, we get negative 5.625 kips. So REX is negative 5.625. And then we've just got joint D reaction in the Y direction to deal with. None of our equations over here involve that, but we've still got that one equation left in our equation bank. RDY plus RCY is negative 5. When we know RCY now is negative, or is positive 2.5, So we've got r dy plus 2.5 equals negative 5. And if we subtract 2.5 from both sides, r dy is a negative 7.5. So r dy is negative 7.5 kips. Now, not a bad idea to look at your answers and at least do one kind of quick sanity check on them. And the sanity check I would do is looking at member DE. Member DE looks a lot like a truss member. Remember that with trusses, you could only exert forces at the ends of the members. Member AB isn't a truss member because it's got a force in the middle of it. It's got two forces in the middle of it. Same with member CF. But member DE is a plain old truss member. And when you've got a plain old truss member, we know something about that. Whatever that member is, the forces at the end of it need to be in equal and opposite directions. They line up with the member. That doesn't happen when you put forces in the middle. But when you only load up a member at the ends, we have that same old two-force member, the plain old truss member. Well, when you break that up into X and Y components, what it means is that the values that you have for your X and Y components when you're dealing with a two-force member should be the same magnitude but opposite directions. At one end, it's going to be down and to the right. At the other end, it's going to be up and to the left, or vice versa. At one end, it's going to be up and to the right, and the other end is going to be down and to the left. Look at our answers here for D and E. Same numbers, but opposite signs. That's telling us that we're dealing with a two-force member. The magnitude will come out the same for both of those. The only time you get the same magnitude at both ends of a member is when it's a plain old two-force member, just like our regular truss members are. So that's a quick little check and something that's come up in a number of the frame problems we've gone over. And if you review any of these in preparing for our exam on Wednesday, take a look at that. Notice that the forces end up being the same numbers at the ends, just different signs. Whenever you have no other forces on the member except what's at the ends. Now, if I went and hung another force on it like that, that would change it completely. It would no longer have that behavior at the ends. So let's find out our magnitudes and close this problem out. Notice that this one didn't have any restriction on how many sig figs to put in. So anything that's reasonable will be sufficient. So we've got 5.625, we'd square that. We've got 2.5, we'll square that. Add those together and take the square root. There I get 6.1556 kips. 5.625 squared plus 7.5 squared. Square root there, we get 9.375 kips. And we'll get the same there. Again, my piece of advice here on figuring out your magnitudes, ignore the signs when you figure out the magnitudes. Don't even bother keying them into your calculator. You're only asking for trouble if you key them into your calculator. Some of them will burn you pretty badly if you forget some parentheses. It'll still dutifully calculate it, but it'll give you, in the best case, a wrong answer. In the worst case, it won't even give you a number for your answer. So just ignore the signs. The signs aren't going to matter when finding your magnitude. So your magnitude should always need to always be positive. And don't forget those units. Any questions on any other problems? Let's see, who do we still have here? Oh, everyone's still on board. All right.